So this tells us something very interesting, which is that what the Wick rotation is really talking about is a rotation. It's a geometrical equation. And in July, we'll come back to this and really probe what this Wick rotation means physically. But as I said, this wasn't understood to the 1950s. And by the 1950s, a lot had happened. So quantum theory had been developed. Bohr and Einstein had had their debate. Particle accelerators had been built. The atomic bomb had been built. Nuclear physics was well on its way. So an enormous amount of practical physics had been done. Quantum theory was highly developed. People were starting to think about quantum field theory before they made this simple realization that's formulated in the Wick rotation. So this is a harbinger of things to come. But before we continue in physics, we need to backtrack in time a little bit and look at what the mathematicians were doing. So across the hall in the math department, 1 year after the Solvay conference in 1929, Kurt Gödel proved his famous first incompleteness theorem. And the theorem states that no formal system that contains arithmetic can be both consistent and complete. And that means that either there are true statements that aren't provable in the formal system, or there are false statements that are provable, or of course both. And Gödel's proof is actually extremely simple. Almost all of the work in the proof is setting up all of the notation and procedures and so forth to formulate within arithmetic the sentence, this sentence is not provable. And once you have that sentence formulated within arithmetic, then the conclusion of the proof is obvious. You know, if you can prove the sentence, this sentence is not provable, then you've proved something that's false. And if you can't prove it, then there's sentences that you can't prove in arithmetic. So this was incredibly bad news for mathematicians who thought that finite discrete operations, which is what proofs are and also what computations are, can exhaustively enumerate the facts. And this was the assumption behind Wittgenstein's claim that the world is all that is the case. The world is a collection of facts. And optimistically, he thought that first order logic would allow us to enumerate all those facts and we'd be done. Dreams of a final theory again. So Gödel's theorem means that no system with finite capabilities, no system that can just do finite discrete operations, can fully describe its environment. It will always be in an environment where there are true things that aren't provable or false things that are provable. But I think more relevant to a discussion of agents is that it means that no agent can describe itself. Any agent's theory of itself will either contain true statements that it can't derive or false statements, or it will either miss true statements that it can't derive, or it will end up deriving things that are false about itself. And of course, we see this in psychology all the time. So an immediate consequence of Gödel's theorem was an intense investigation of what computation actually is, what it meant to talk about finite discrete operations. And two leaders of this were, of course, Church and Turing, and here's a picture of a Turing machine, and they defined a computation as a process that can be implemented in finite time by such a machine, or by Church's lambda calculus, or by any of the now hundreds of other methods that are provably equivalent to a Turing machine. So what does this mean? It means that computation is a physical process that can be mechanized, and it turns out mechanized in any one of a huge array of ways. It means that many different implementations of any computation are possible. So I can do it on a Turing machine, I can do it on my laptop, I can do it in my head, etc. The most important things it means is that there are questions with no computable answer. This is the revenge of Gödel's theorem. And two of the most famous questions of this kind are, given some arbitrary program, will it halt? Will it get to an answer in finite time? And the answer to that question is, this is undecidable. No procedure can figure this out. And the other undecidable question is, given some arbitrary program, what function does it compute? And you'd think that would be simple, that you can read a program and figure out what function it computes. But it turns out that is undecidable. That cannot be done by any finite process. So this was another body blow to the goal of understanding everything with finite discrete processes. But it also set the stage for something new. It set the stage for thinking about an agent who interacts with a computational process by giving it an input and then looking at its output sometime later. And this, of course, will look familiar because I've included the blue ellipse, which is the boundary, which these days we call a user interface. And the user interface just allows some finite action on the system and then the ability to observe some finite response by the system. So we can now ask, what can Alice determine by acting in some finite way and then making some finite number of observations, i.e., receiving some finite number of outputs from the system that she's acting on? And the first 20 years of this produced a large number of answers, all of them negative. So to go back to Turing, he proved that Alice can't tell what's implementing the function that she sees being implemented. She can't tell whether a given input will lead to an output. That's the halting problem. Shannon showed that Alice can't tell what the inputs mean to the system. His whole theory of communication is completely independent of semantics. And his theory of communication actually accurately describes what Alice can observe. Rice is the one who proved that you can't determine what program is generating the outputs. And then Moore proved a very similar result in a completely different formal setting of general cybernetics, that you can't tell what process is generating the outputs by finite observation. But what Alice can do is build a predictive model of what generates the output she sees in response to her inputs and test it by designing new inputs. And this is, of course, as Karl Popper told us, the process that we call science. So Alice can do science even though she can't answer any of these fundamental questions. Now, this, of course, has a huge technological consequence. Since this theory of computation tells us that processes are effectively virtual, we don't know what they are, and we can't determine what they are except in theory by making the theory. Technologically, it means we're free to use virtualization everywhere because we have to deal with it anyway. And this allows us to build multi-level architectures. It means that we can architect computers where no layer of the computation has any idea what's going on below or above it and doesn't need to. And that's what makes practical programming possible. So from these no-go theorems that tell you what you can't do, you actually get an enormous boost into it and use to probe the world and develop theories and on and on and on. So in a sense, Gödel birthed not only computer science, but practical computing by showing us that virtualization is just the way the world works. So now let's go back to physics, where these ideas were replicated, basically reintroduced, reinvented by Feynman in developing his path integral formulation of quantum theory. And basically what Feynman realized was that in any physical process, the observer, Alice, prepares some state that she's interested in. She prepares some input to an experiment. Then she lets something happen, and then she sees what the result of the experiment is. And the canonical experiment in physics is scattering. You fire two protons at each other and they intersect someplace and stuff comes out, and you measure the stuff that comes out. And what you can measure is momentum and spin, energy, things like that, position. So these processes conserve the total values of the things you can measure. So in particular, they preserve momentum and angular momentum, and they preserve, other things that are harder to measure and are only approximately conserved anyway, like lepton number. But Feynman's contribution to this way of thinking about experiments was to say, look, if you want to understand the output, you have to sum over all of the possible processes that could have produced the output from the input, no matter how improbable they are. So the famous idea from Feynman diagrams is if you have an electron that's scattering off an atom, you measure the initial state of the electron that you've generated with an accelerator or something, and you measure the final state, which involves momentum and spin and so forth. And for all you knew, partway through the process, the electron disappeared and an entire universe appeared, and then annihilated with a copy of an entire anti-universe, and the electron came back out. And you have to include processes like that if you really want to understand and correctly predict the outcomes of your measurements. And Murray Gell-Mann lifted the bumper sticker slogan from T.H. White and the Once and Future King, everything not explicitly forbidden is mandatory. That sums up Feynman's idea. And this is called the totalitarian principle, since it's what's written in T.H. White's book on the kingdom of the ants, for which everything not explicitly forbidden is mandatory. So let's think about a real example that's a bit, actually, it's the same as scattering. The ultimate scattering experiment in physics is a black hole. Stuff goes into the horizon, stars, whole galaxies, whatever. Something happens and stuff comes out. And what comes out is Hawking radiation. And information is conserved if the information in the Hawking radiation is actually the same as the information in the stuff that went in. And conservation is not qualitative, it's quantitative. It's only the quantity of information that's supposed to be preserved. And you can ask, how much is the information that's being emitted by a black hole that's emitting Hawking radiation? And Bekenstein was the one who figured this out using an incredibly simple argument, but I'll just give the answer here. The answer is that the total entropy of the black hole is its area divided by 4. And the area in this equation has to be computed in Planck units, which are units where Planck's constant and the speed of light and Boltzmann's constant and other interesting things are all set equal to 1. So 1 Planck area is the Planck length squared, which turns out to be about 10 to the minus 70th meters squared. So this says that black holes are the most entropic entities we know of. So a black hole about this big, with a radius of about a meter, has an entropy of about 10 to the 70th, which is, of course, an astonishingly big number. And a black hole with the area of the sun, so a moderate-sized cosmological black hole, a real thing that we can observe with has an entropy of about 10 to the 79th.